Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Very good afternoon. Boleh dengar saya ke kelas?
Boleh dengar.
Alright, sorry ada kind like technical problem so little bit late I start. Okay, kelas okay, firstly selamat Hari Raya Maaf Zahir Batin. So we still in online class. So this would be the continuation from our previous topic, which is fatigue analysis, fatigue failure in component design. So I already explained to you during the first meeting on fatigue failure. Little bit I explained to you about the fundamental of fatigue analysis. What is the equation we should use to get the basically about the fatigue loading and how do we calculate the endurance limit SN. And also how do we roughly we discussed on the previous in the previous example how do we get the safety factor for our fatigue analysis. Because if you remember in the previous example that I shared to you that on the previous exercise safety factor, as I have just a quick one, but I have not yet explained to you why is this safety factor is like this. Because fatigue analysis, for fatigue failure, because in analysis in fatigue failure, we basically we need to find the safety factor, but the safety factor is not just n like that. We based on sigma EA over your sigma EA over what over your sigma EA over your sigma EA over your SN plus your sigma EM over your SUT is 1 over your safety factor. That's the basic formula. So why is this formula like this? Why is our fatigue factor? Why is the safety factor is not just simply because, as I told you, when we find the safety factor, the upper one is the strength. Because fatigue analysis, the strength is not SY, we use endurance limit. And so why we are not doing this like this one? We have sigma equivalent based on DET. Yeah, basically this is just a basic, this is a right. I didn't say this equation is wrong, but this is sigma equivalent because remember, when we do fatigue analysis, we have alternate because our fatigue stress that acting on our component that we do analysis sigma over time is not just remain like that. They have a kind like this sine wave where we have sigma mean, the average, and also we have the alternate value sigma ALT or sigma A. Because if we consider this, so what should we put here? Because this is, we don't have what is the value of alternate and mean. So that's why the equation become like this, because we consider, because all fatigue analysis, we should find the mean and also the alternate. So you cannot suppose which one's supposed to be in this denominator. So that's why the equation is like this, sigma EA over your endurance limits. Remember, endurance limits is your endurance limit. It's not we, because in fatigue failure, we don't, our strength is not SY. We have to calculate the endurance limit. So endurance limit, so what is the endurance limit? Endurance limit, as I have mentioned to you in the previous class, we have multiplication, modification factor times the Sn prime. So at the end here we Sn prime. Sn prime is RR more test. RR more test is standard test already. They have the, okay, from RR more test, because RR more test, when they do for steel, if I show you this figure, the strength over the cycle. This is 10 to the power of 3. This is 10 to, this is a log 10 graph. They plot the data steel material because most of our component is steel material. Class, can you hear me? Class, I just keep asking. Boleh dengar saya ke? Class.
Boleh.
SN curve, because still they already conducted the test, RR Moore test is a standard test. 10 to the power cycle, it is a log 10 graph, not typical graph, log 10 because they are scale up, zoom in version. So we plot, we have here is SUT because when kind like one cycle, zero cycle, the ultimate one that could cause the ductile, even ductile material to fracture, to crack is the most ultimate of that material. You can get from the table properties, any material, SUT. It crack, it means failure, not yielding, just failure, it means crack, SUT ultimate. That is when no cycle, like static loading. The one you apply, overweight, the loading, the stress, up until SUT value, then only will crack. But when you go to 10 to the power of 3 cycle, it become, the graph become like this, straight line. But you go for, when you have 10 to power of 6 cycle, like the shaft is rotating, when it's rotating 10 to the power of 6, the strength of that specimen is lower. So we have a straight graph like this. And after 10 to the power of 6, it become constant. Okay, from RRD is RR Moore test on material on steel. For example, on steel, ductile material. Steel is ductile material. Even aluminium also ductile, but steel, because we focus on steel, because like shaft, bracket, mostly is steel. They found that this is straight for 10 to the power of 6. 10 to the power of 6, this is infinite because this is what we call infinite life. Can you see? My video boleh nampak semua. This is infinite life. Infinite life. Above 10 to the power 6 and above is infinite life. This is considered finite life. Finite life. Below 10 to the power 6 means finite life. Okay, from here, it discovered that this is value of Sn prime from standard RR most. It discovered that this value is actually 0.5 of your SUT. This is SUT, half of it. Sn prime for steel material, for steel is 0.5 SUT. So this is a standard test. So that's why in our equation, our case, we need to use the standard test, then we multiply with the modification factor to adjust to our situation. In our case, for example, in your assignment or in test question. So that's why our Sn, this is Sn from standard RR mode test. So we need to multiply our Sn that we calculate endurance limit. This is what we call endurance limit for our case. For endurance limits for our case, Sn, so we need to do the modification factor Cl, Cs, Ct, okay, Cl, sorry, my mistake. I missed Cg. Cg is a gradient factor. Okay, Cl, Cg, Cs surface factor, Ct temperature factor, and Cr is the reliability factor. Multiply the standard Sm prime. This is RR mode. Okay, this is RR mode test 0.5 SUT for steel. Because SUT, your material you can find from the at the back of your textbook table properties. You can get the SUT value. So your Sn prime is 0.5 SUT. So this one is Sn prime is RR mode is 0.5 SUT. So you multiply, adjustment factor, modification factor based on your situation, because loading is bending, you have one size factor, the size of the shaft, certain range, you have 0.89, surface factor based on is it grinding or is it machine or is it polish, so you have different surface factor, temperature, what is the temperature of your system, the shaft you analyze, what is the temperature condition when it is running, that is temperature factor, and reliability factor is 99%, that is a value of that factor. So we modification, this is what we call CSCG is all the modification factor. So we get our Sm prime in megapascal. So that equation, so that's why you want to find safety factor, the basic safety factor for fatigue analysis, sigma E, this sigma E amplitude, alternate, because fatigue failure, you cannot just use the basic equation sigma E at the bottom here. So you have, because we have alternate like this, all situation of fatigue analysis, they have a sine wave. They have an alternate value, and they also have the mean value. So that's why sigma E over your Sn, because Sn we have already calculated. Because this one is straightforward, you can find it at the first place, right? So you get the value in megapascal for your Sn. So Sn will be your denominator plus sigma E. Sigma E next sigma equivalent. Sigma E mean. Sigma E mean is the mean average. One is alternate, one is average. So average here over your SUT equal to 1 over your safety factor. So safety factor in fatigue analysis, we use Goodman because they have one more theory, Langer based on yielding. I explain to you. So this is your calculate for Goodman based on Goodman theory. Actually called modified Goodman theory based on that. NG means safety factor. So sometimes you find this, and sometimes you have to find both. Another safety factor is sigma EA over SY. Also, you need to check sometimes if the question asks you, and sigma E mean over SY equal to 1 over N Langer. Langer mean it based on yielding. I explain to you. Okay, this is a main equation. If you find that sometimes they ask you to find based on yielding because our denominator is based on yielding. You know to limit either sometimes our point is it's safe in Goodman, but sometimes it happens it over the yielding point. Also, you must take note on that. Okay, why is this equation like this? Okay, please, okay, line okay, class, are you there? Boleh? Video okay?
Boleh.
Right. Okay, this is a standard SN curve. Standard SN curve. Okay, this is standard RR test. Okay, when you do, because when you do, you want to find safety factor because your specimen you do analysis like shaft, bracket, anything. What material that it use, and so what is the strength is their endurance limit. So because since this is SN curve, when we, because remember we have sigma equivalent alternate and sigma equivalent mean. So what is that sigma EA and what is sigma EM? Remember, if I hold on, if I share you Control Shift D, share Control Shift D. Hold on. Share Control Shift D. Okay, Control Shift. If I share you where is my, hold on, okay, from the textbook, hold on, it's my textbook. Saya ni tak faham lagi gunakan Webank. Share the, hold on, where's my textbook? Okay, can you see my textbook? Am I sharing the textbook? I'm scrolling right now, page 301. Plus, are you watching now? You can see, right? Okay, you can see this is a textbook. Okay, you must highlight this thing, textbook on your page, Javina textbook 301. So because remember our sigma EA, remember the previous, we already discussed this, we combine sigma EA is sigma amplitude plus 3 tau A squared. And sigma EM, because in our case, we have sigma and also we have torsional stress. Sigma can be mainly bending, it's a combined plus sometimes it's axial. Later we will discuss about one sample problem we need to discuss with you. Okay, We need to find the sigma E alternate, and we need to find the sigma E. What is E? E mean we are using von Mises, right? Von Mises. This is actually the extract from von Mises, right? Because since we have alternate and we have mean, so that's how they put things here. Sigma E alternate square root. So this is a question you must take note. This two is very important. You must find sigma EA and sigma EM. So remember in the previous example, we already discussed in the how do we find the sigma EA and how do you find the sigma? Sigma E mean is sigma mean over 2 plus square root tau mean and sigma mean. Sometimes remember tau, for example, like for shaft, tau we have mean value, we don't have alternate. For shaft normally for torsional stress, because torsional stress a long time, torsional stress remain constant, it means they don't have alternate. So here, alternate for here, 0, right? So, okay, now you got sigma EA, sigma EM. Now, if you look on back on my video again, okay, let me stop sharing. If you look on my video, live video, so that's why the sigma EA, so the equation is like this, right? Sigma EA, you find it here, and sigma EM, you find it. So Sn, you already calculate, and as you calculate, that will be your safety factor. So that's how things work. Okay, that's how things work. But okay, why this question is like this? Okay, I need to explain to you about this thing. Okay, this is a standard armor test. When we plot sigma EA, so why is why is this question like this to get the safety? Because when you plot sigma EA, sigma EA, your sigma E equivalent alternate, and your sigma EM. So this one is sigma EM. This is sigma EM, sigma E mean. This one is sigma E amplitude. Sigma E amplitude and sigma EM. So the border of here from Sn from 10 to the power of 6 cycle. So we have Sn 0. Okay, your Sn that you calculate here, your Sn that you calculate here, CLCG. Okay, so your Sn will be here. So this will be Sn. Okay, this will be your Sn. Okay, let me make it a little bit lower. So this will be your Sn curve. This will be your sigma EA, sigma E mean plot, Sn. But sigma E mean, the border is SUT. It is sigma E mean graph. Sigma E mean, the border is SUT somewhere. T is the value of FUT because bigger, Sn little bit lower. On y-axis, sigma E amplitude. Sigma E amplitude. Sigma E amplitude mean, okay, that one is, what is mean? So alternate, this is sigma E alternate. Sigma E alternate mean, because when you have this thing, right, this is your stress. So this is your sigma. So sigma E alternate. So this is sigma E alternate, this value. This value, when it reach to the border of it to become parallel, this ultimate value. Sometimes graph can be like this. Sometimes when you are in completely reverse, like shaft, you have pure bending only. Your graph can be, your sigma can be like this. This is completely reverse, where we don't have like this case. We have mean, we have sigma E mean, but sometimes like shaft pure bending, for example, you have a shaft rotating, support by bearing, and we have a bending load there, and just a rotating shaft. Your bending stress is completely reversed. So in here we have sigma, we have only we have only sigma alternate, but our sigma mean is 0. Okay, our sigma mean is 0. So it means that this sigma alternate, or we call sigma E, equivalent alternate, in completely reverse, if this alternate value either in this case or either in this case, or either sometimes it can go to negative side compression. So you have what I mean is your sigma EA, the value of the alternate value, not the mean, alternate value. So the border of it, sigma E, it can reach, if it reach the Sn value, that is their most upper limit. So this is that's why on your y-axis is sigma E alternate. Sigma E alternate. The border after Sn it will fail. So this is the border. So this is a line. But this is a line of sigma E mean. Mean means what? This is mean. Your sigma E mean, the average. Average sometimes average can go for negative. Sometimes your stress all is negative compressive, compressive stress. This is sigma E mean. It can go for negative side, it can go positive. Okay, let's say consider positive side. Sigma EM is positive. This one is negative side. Okay, for positive side, like this, for example, like this is your graph, your sigma E mean, the average value, it cannot reach the SUT. The average value cannot reach SUT because why? Average, because you have sigma maximum and sigma minimum. You are talking the mean, the average stress. You have maximum, but you're taking the middle of it, the average. The border, it cannot reach up until it breaks. I'm not talking about yielding, about it break, is SUT. The alternate, it can go, the alternate is the distance max minus minimum divided by 2. This is the alternate value. The alternate value sometimes is bigger, sometimes it can go bigger like this. It can go bigger like that. Your alternate it can be, your graph, your alternate it can go bigger like this. Understand? Bigger, so big like that. So this is your sigma E alternate. This alternate, this distance, the limit is the endurance limit. Understand me, class? Sn value that you calculate. Sn is CL, CG, CS, CT, CR, Sn prime. So what the maximum limit that it can goes before failure is Sn. Understand? But the mean, this is mean. Sigma E mean, the largest that it can goes is SUT, ultimate tensile stress of your material. So that's why our graph, the limit of sigma EA and sigma EM just now is like this. Sigma EA is Y, sigma E mean is x-axis, sigma EA is Sn, the limit, the alternate limit is Sn, but for sigma EM value, the limit is SUT. So we have the graph like this straight line. So this means our border. When we plot sigma EA and sigma EM, so in whatever our case, when you do your analysis, you calculate sigma EA. Let me share you again. You calculate the sigma EA. Like in this equation. If you see at this expression, sigma EA, let me erase this back. This equation, make sure you highlight in your textbook what I mean these two equations. See, you calculate sigma EA, okay? You calculate your sigma EM. So whatever sigma EA that you calculate is within here, okay, sigma, okay, because this is sigma EA. So this is your sigma EA you calculate, and this is your sigma E mean that you calculate. All right, so this is your point. So it is below because this is the border, right? So it is below. This is how you can find safety factor by using graph. So this is your loading point. This is 0, 0 point. Loading point, so it means like this. This is your point. Start from 0 like this. So safety factor is like this. You can use graph also. Safety factor, because this is the border of your failure. This is the border of your failure. So safety factor also you can use by graph or you can use by, so that's why the equation is like this. Because sigma EA over Sn, sigma EA over Sn, sigma EM over SUT, sigma EM over SUT equal to one of your safety factor. So that's how it works. But if you plot graph here, you plot graph already. This is your sigma EA that you calculate, sigma EM you calculate based on this equation in your textbook here. Okay, in your textbook. Guys, you can watch my live video. You can watch also, right, class? Just asking. Class. No, like my live video, my hand. Can you see? I'm sharing both, right?
Yes, can.
All right. All right. So you can also calculate by using this graph also. What is safety factor? Safety factor based on Goodman. We call it is Goodman line. This is what we call Goodman line. Goodman line. Okay. Goodman line. Safety factor, you can use graph also. And safety factor is your here, you plot, because this is the border of your failure. So this will be your SM, because this is sigma mean. So strength mean on your case, because your loading point is here. So you extend it up, so this is the border. You extend it up until it intersect, this is the border of failure. So this distance is SM. The one, the border, you bring it down SM. So your sigma EM. So safety failure can be SM over sigma EM. Also can formulate. You can calculate by using graph. And also if you're using y-axis, sigma E alternate, okay, this is your border. So this will be your strength alternate. Strength alternate over also equal to strength alternate over sigma EA. Also you can do it like this to find safety factor. But because based on this line, basically mathematical representation of that is here. Understand that, class? This is the mathematical. You can use directly straight away the formula. Calculate your sigma EA from this textbook. Calculate your sigma EM from here, equation A and B here, sigma EM. Then over your SN, what's why your SN? SN is CL, CG, CS, CT, CR, SN prime. SUT, get from the table properties, what material that you analyze on, get your SUT, ultimate tensile strength. So that will be 1 over your safety factor. That is good math. Okay, that is good math. But, okay, another case, that's how we find safety factor. But another case, okay, let me draw this again. Let me draw this again. We have sigma EA, we have sigma EN, sigma EE mean, sigma EA graph. So our Goodman line is SN here. Here is SUT. Okay, this is our Goodman line, but SN is lower than SY. So this is SY is much greater, because remember SY, when you do analysis where you don't kind of like static loading, it means it's not, your stress is not fluctuating. You don't have high cycle, low cycle. It means static loading. So SY is greater. Sigma EA, even in your case, even your sigma EA, our border just now I mentioned that sigma EA, if you go for high, different, very high sigma E alternate, what it can go cannot go more than SN value, right? But sometimes, but it exceeded, okay? Sometimes it I'm not sorry, not sigma A, your sigma EM, the limit is SUT, right? The average, the limit is SUT. But SY, if you look, SY, even your sigma E mean, your SY yield strength is actually lower than SUT. Yield strength is actually lower than your SUT. So this is your yield strength. Yield strength tensile, because positive side tensile, I put it tensile, negative side compression. SYT. So we have a border we need to consider. This is a straight line. Class, are you with me? Class, are you there?
Yes.
Okay, actually, our border, our area of safety is here actually. At the beginning, you somewhere here, right? But we need to calculate both. SYT sometimes, because why? Sometimes your point is here. Based on Goodman, okay, this is your leading. Your point is here. Based on Goodman, dia selamat. Because Goodman line is here, SN, SUT. It's within the region, right? Within the region, if you zoom in here. But it crossed the SYT. But your sigma EM already over your SY yielding, because this is your limit of yielding happening. That's why this equation for Langer, because this is our borderline, for Langer is based on yielding. Langer is based on yielding. So sigma EA cannot go SY tensile, SYT mean tensile strength is SY value. Sigma E mean cannot go more than SY. Do not confuse. Tensile mean positive. Cannot go to SY. Okay, both EM. Because this is our line border. So this is 1 over your safety factor L. L Millinger. Okay, sometimes the question asks you to find both. Sometimes based on Goodman, because this is equation on Goodman is what just now? Equation on Goodman Goodman theory. So this is NG, Goodman theory, sigma A over N to the limits and SUT. It's safe. It kind of like 1 point something is safe, but based on Langer, it is less than 1. I mean, it's happened to leading because your error is somewhere here. Be careful about, you need to check. Okay. Boleh kelas, faham That's how we calculate the safety factor. You can use by graph, as I mentioned to you just now, like this. Okay, you can use simply direct equation like this, and based on Goodman and also based on Langer. Langer is based on yielding. Sometimes you need to find both, depend on the question how it asks you. If you just find the safety factor based on Goodman, you straight away use this equation. But sometimes you need to check. Okay, you need to check, especially your project later on. You have project, you need to check both. Okay, paham kelas do you understand me? Do you understand me or not?
Yes, doctor. Understand.
All right, good. Okay. Okay, as I have mentioned to you, our equation, okay, let's say we focus the main equation, Goodman, right? Okay, if you look the one that I share you, this textbook, right? Sigma EA, sigma A plus 3 tau A square, sigma EM, sigma min over 2 on this one, this textbook. Okay, actually, sigma here, if I zoom in this one, this sigma alternate, this all about alternate. A means alternate, M means mean, M means mean. But alternate here, you cannot, okay. For example, you have a shaft. Remember, you have a shaft, and when you have a graph, you make a shear diagram, moment diagram. So you calculate the bending stress. Remember your bending stress. Okay, because sometimes we need, okay, this is a thing that you need to, another thing that you must do it, because not just simply you find sigma A, because all the sigma alternate, tau alternate, you need to multiply by the fatigue stress concentration factor. Why? What is stress concentration factor? Okay, you take note on this. Because when you do analysis, for example, like shaft, if I zoom in shaft, they have kind like this, they have a groove, notch, a groove. Whenever you have a groove, for example, a shaft, this is a groove. This is what we call a groove. Can you see my video? Boleh Class, Okay. Okay, the shaft is normally the previous example that we already discussed in the previous class, that is plane diameter, but most of the case, especially in exam, is not plane. Shaft, they have geometrical shape like this. They have a shoulder and they have like this. They have something like this. Okay, your shaft, they have a groove and they have a shoulder. Okay, we have a groove. Okay, we have a groove. Okay, some of the case you need to focus on this thing. Because if you plot shear diagram, your maximum moment could be here. You understand what I'm talking about? This is your free body diagram. Shaft, this is your moment diagram. Moment diagram. You may remember you do shear diagram, you moment diagram. Moment maximum at here, at this point. But if you look, if your shaft, geometrical shape is not a plane. If your shaft is just a plane diameter, you take the maximum moment. That one is the critical at that point. But if your shaft, this is center line of your shaft. Shaft is not just a plane. Shaft, they have shoulder. For example, we have bigger diameter here, and we have smaller diameter D here. Capital D is bigger diameter, smaller diameter. So here, we have shoulder. When we have shoulder, we have fillet. We have fillet. Nampak tak? We have fillet. It means here we have radius. Once we have fillet, we have notch radius. Here we have groove. Okay, what's the purpose of groove? Okay, shoulder, what was the purpose of shoulder? Because shoulder, like the left or right, it's kind of like this. When you mount a pulley, Clark, can you watch my drawing, class? Can you see my live video, class? Class.
Can.
And
I see.
Kita mount the pulley. Pulley mounted at the shoulder. Because why do we need shoulder? Because shoulder, that means the pulley cannot move to the left. It's blocking by the shoulder, right? No such thing. Your shaft just plain and you mount pulley. Pulley to sometimes it can slide. No, nothing is locking the pulley to shift to the left and to the right. So to block the pulley to shift on the left is the shoulder. To block the pulley to shift on the right is we have a notch and then we'll snap a snap ring here. a fastener kan, what we call it, I cannot recall that. Mechanical component is a ring and a snap it at this groove. Understand that, class? And that's why the shaft have a groove. So you mean your shaft is not plain, right? They have this geometrical shape. So whenever, okay, notch, shoulder, we have notch radius. Groove, can you see? We have notch radius also. If this is the case, you cannot take, okay, let's say even in your shear diagram, your moment diagram is the most critical here, moment maximum here, moment diagram. You cannot take this as critical because since we have notch and we have notch here, you need to identify both. Understand that? So you have to go like this because since you know your moment from your moment diagram, you can find your moment from your moment diagram, from shear diagram, moment diagram. You can do theorem Pythagoras to get this moment at this shoulder and moment diagram at this groove, at groove. Understand? You need to find this. So you need to analyze on it. Because this is critical. Why? Why is this critical? Because we have a notch. When you have a notch, it means, okay, let's say we focus on the shoulder. When you focus on the shoulder, for example, the shoulder, guys, kalau shaft, you have a shoulder. Okay, this is part of your shaft. I draw it like this, and this is your smaller diameter. Remember this shaft, we have smaller diameter, bigger diameter. So let's focus at shoulder. For shoulder, we have a radius. We have a kambi, fillet. We have a fillet. It's not like the plane. We have fillet. Whenever when you have a kind like fillet like this, you punya, okay, let's say you punya bending stress, guys. Kalau bending stress, kalau you punya, okay, if plane diameter, okay, let's say at the same section, when you have happen to have bending, let's say we have bending, our stress distribution is like this. Okay, with this one, we don't have any notch, any fillet, we don't have a shoulder, just a plane diameter. So this is neutral axis of the shaft. So here we have tension. When we have bending stress, bottom lower level of your neutral axis is compression. Our stress of sigma bending is like this. It is MC over I, or 32 moment pi d cube for solid shaft. But in your case, if you have here, you have a notch, and you have a bending here. Okay, you have a notch because of this fillet notch. We have the, when happen bending there. Okay, this when happen when you have a bending, the stress distribution is not typical like this, guys. It's not typical like this. It's not like this. It is multiply. It kind of amplify at the notch. I mean at the notch, if you look, it kind of amplify. It elongate a little bit, and then after below the notch, we have a plane diameter of shaft, then it becomes straight. But this one is compressive side, right? Straight, but here is level of the notch. The stress distribution is elongate. Nampak tak, guys? They elongate little bit. Faham tak, class? Here, at the notch here, the stress distribution is elongate. Faham tak, class? They extend little bit. Class, do you understand me or not? Kalau normal case, like this, no notch. Kalau dekat shoulder ada notch, it elongate little bit. That elongation factor, that is a stress concentration factor based on, so we need to find that KT value. KT value is a static stress concentration factor based on what station. In this case, is shoulder. Also, same goes for the groove. For plane, for groove, okay, plane shaft, kalau plane shaft, like I show you just now, it's simply like this. It's simply like this. If you have a groove, okay, a groove where we have a notch, a groove, like this. I mean your shaft, you have a lekuk kat sini. Okay, you have a groove. So you have a radius R and you have a smaller diameter here. So when you have bending happen that at the groove, you see this is the groove. Here it elongates more. But the stress distribution then only it going kind of like curve, then it goes straight line. This one compressed, but this one it elongate. That elongate compared to non-groove plane diameter. What is that factor? So this is what the stress, when you have a groove, the stress concentration factor is much higher. This one go, understand, class? I'm talking about class. Faham tak, class? Hello, class, are you there? Clear? Faham? They elongate. they elongate a little bit. So that's why you need to find, because you cannot simply use just calculate bending stress like that. You need to multiply your bending stress, either it alternate or it mean, okay, your bending stress or your torsional stress or your axial stress need, in my case, as explained to you, is bending case. Same goes for axial stress. Same goes for axial. Kalau you, okay, this is your shaft, plane shaft. Same goes here, not just bending. Sigma axial stress is F over area, right? Axial. Sigma axial. Kalau you don't have any notch, just a plane diameter, memang of course you don't multiply with fatigue stress concentration factor, just sigma F over area, bending axial stress. But if you have notch here, you have a notch or you have a shoulder. Pasal kalau plane you punya, kalau plane stress, kalau just no notch, just plain diameter, you punya distribution of your stress is like this lah, just a straight line like that. Normal je, axial stress. Axial stress. But if you have plane, kalau you have, if you have groove on your shaft, even this groove, or shoulder just now, that's why I show you groove. Okay. Okay, this is your, you only have direct axial stress. So your sigma axial is F over area. So here, at the notch here, because this is our radius of the notch, here it extend little bit, elongates. And then the curve, then it go for average, F over area. But this one, extend little bit. Understand that, class? Even for axial stress, because of this notch. When you have notch, a curve, small radius, it kind of like, we have a stress concentration on that. It kind of like elongate a little bit. So this is higher. So that's why they have a factor there. They have a factor. So what is that factor? The factor to, okay, because whatever bending stress, like for example, in this question, sigma alternate, you find bending stress, you need to multiply by Kf. Axial stress also, you need to multiply by Kf. Torsional stress also. Even torsional stress, guys. Torsional stress also, if you have a notch, even, okay, if you have a shoulder, okay, shaft with shoulder, we have knee, even your torsional stress also need to multiply by stress concentration. For shoulder, we have, okay, we need to multiply. So whatever your, for example, you calculate your bending stress is 32 moment pi dq for solid shaft. So you calculate in megapascal. Okay, but that is not yet. This is only raw bending stress. You need to multiply if you are at the shoulder. If you are at the shoulder, for example, like I explained to you just now, in this case, you are focusing, because this is your moment diagram. You know your moment here. You know by theorem Pythagoras what is distance from shoulder to here. You can find it. Theorem Pythagoras. Your moment at the shoulder. So you know moment at the shoulder. So this will be your sigma bending here is 32 moment at the shoulder. Okay, moment at the shoulder pi d cube. This is sigma bending, but this sigma bending need also to multiply. Not just here, okay, shoulder even is less than the most critical case, but even less. But this thing, 32 moment at this shoulder here, pi d cube must multiply the Kf value. Kf means fatigue stress concentration factor. So what is fatigue stress concentration? Okay, fatigue stress concentration factor. Tolong jap. Saya ada rekod ni. Nanti korang see my recording video kalau korang tak faham. Jadi how I teach kelas, saya tak based on PowerPoint slide terang you takkan faham. This how I explaining. Boleh? Boleh buat? Kelas?
Boleh.
Boleh, Doktor.
Kalau saya tunjuk PowerPoint slide, you boring. You tak faham. This how I explain. I already record, nanti I share. The previous guy, nanti I share in YouTube, previous class. And this one also I'm doing recording, then I share it again. Okay. Your bending stress need to multiply. Whatever bending stress you find, bending stress for, this is for shaft, guys. Do not confuse 32 pi d cube, right? For this moment at shoulder, faham tak? In your shear diagram, moment diagram, not moment at the critical, at shoulder punya level, you can get it. Theorem Pythagoras. A moment at shoulder, okay, you get in megapascal. What is the diameter of, this is the smaller diameter. You asking me, sir, which one at the shoulder? Okay, this is my shoulder, right? So I have this small radius. At shoulder, this is R, I have bigger radius, and I have here is small. So at shoulder, sir, which one pi d cube? Which shoulder? The smallest one, not the bigger one, because critical is the smallest cylinder. Okay, this is only the raw in megapascal you already calculate, but this bending stress need to calculate by fatigue stress concentration factor. So what is that fatigue stress concentration factor? Basic equation is KF. KF is stand for fatigue stress concentration factor. So what is the equation? Is 1 plus Q to the bracket KT. Okay, KT is a static stress concentration factor. Actually, in the previous chapter that I explained to you, static stress, we are not focusing on stress concentration factor because stress concentration only be introduced in this fatigue. All right. But in fatigue analysis also, if happen, you have this, you need to multiply static stress concentration factor. Okay, we need to KT minus 1. So this is a basic equation. But KF depend on bending. You have to find KT bending. Okay, I show you for example. Okay, like this. I show you example. All right. Okay, straight away because we are already 301. Ni saya non-stop boleh kelas? Non-stop kelas. Kelas. Are you listening? Saya non-stop lah. Kelas.
Boleh.
Right. Okay. I just show you terus kita discuss example. Okay, can you let me stop my sharing? I need to share you. Okay, in the e-learning. Okay, hold on. E-learning. Open your e-learning. Buka e-learning, guys. Okay, e-learning. Okay, e-learning you tengok guys. Kelas e-learning topik saya lupa lagi. Ni one in-class exercise fatigue and also the solution. Both of these. Nampak tak kelas? Ni one in-class exercise and this is the solution. Let we discuss. Okay, then you will see this exercise. Tengok sini. Tengok ni. Okay, can you see my PDF ni? Soalan ada nampak tak? Kelas. This one.
Nanti tak tahu.
In-class exercise. Ada nampak kan? Okay, you maximize, you boleh nampak maximize the view. Okay, this the question actually from the previous test. Okay, this exercise, in-class exercise actually. Okay, we have question 1 here. Okay, not this one, this question 2. I'm talking about this question 1. Fatigue analysis. Okay, we have this shaft. Okay, kalau tengok figure 1 shows. Okay, figure 1 shows a shaft with 2 pulleys for the power transmission purpose. So this shaft is a part of power transmission. It's a middle shaft. Actually, they have 2 shafts and things like that. Okay, in this shaft, they mounted a pulley at A and another pulley is at B. Right? Pulley at A and B. Okay, the shaft, of course, it not hanging in the air, must be supported by bearing at O and C. Okay, mean at C and O here must be bearing. All right. Okay, it also stated that the shaft is AISI 1045 hot rod, the shaft. Because we are analyzing the shaft, not the pulley, the shaft. Like for example, then you do shear diagram, right? Moment diagram, okay? The shaft OABC, okay? Material of the shaft AISI 1045. So it means that you can find the value of your SUT because for fatigue analysis, we don't use SY. Yeah, you use SY. You find SY so because based on class, are you there?
Ya, Doktor.
Okay, hold on jap. Kenapa my video stop? Sekejap my video. My live video, I need, hold on jap. Okay, let me resume my recording. Okay, class. Okay, we continue. Okay, if I already shared the, I did share the, okay, I share again the apa tadi? The exercise tadi. All right, the exercise, question 1. Okay, it said that AISI, the shark is AISI 1045 hot roll. And okay, the point is, okay, if you look on my live video again, okay, if you look here, okay, the first step when you do fatigue analysis, okay, this is a procedure that is first, okay, we know because tengok sini, the idea is, okay, determine whether the child will have infinite life. To the, you mean safety factor lah. Okay, you want to find the safety factor. Okay, let me adjust my video. Okay, basic step here, of course, fatigue analysis, we need to find the sigma EA over your endurance limit. So this is the first thing you should, this is a thing, because we need to calculate the safety factor. The equation for safety factor are not always good based on Goodman theory, plus sigma E equivalent mean, sigma E alternate over your SN. SN you can straight away find it, plus sigma E mean over your SUT. SUT because it's given AISI 1045, although you can get on table properties. What is your SUT? Equal to 1 over N safety factor based on Goodman theory. So this is your safety factor. So that's the point. This is a post of this. You need to find the safety factor. Greater than 1 means it is for infinite life. Because what we did here is based on infinite life. Greater than 1 because based on infinite life. All right. Okay. We need to find the sigma EA, right? We need to find the sigma EM. Okay. Before we do that, okay, this is your main equation. Okay. The first move, what you should do first, straight away, you can calculate your SN. SN endurance, you can straight away calculate it because it's already there. Because SN will be in the denominator of our safety factor equation. So the first move, what you do, calculate your SN. You calculate your SN. So what's SN? SN, endurance limit is CL, CG, CS, CT, CR, SN prime, right? Okay, SN prime is 0.5 SUT. So what is stated there? Okay, guys, open your textbook, get me what's the value of AISI 1045 SUT. That's why you need to find the SUT. SUT berapa? Class, are you there? Class, are you there? Class, are you with me or not?
Yes, sir.
What is the SUT value? Cepat sikit. SUT berapa? Berapa kelas? Berapa? Table appendix C. Appendix C. Cepat sikit. Saya nak you guys practice. AISI 1045 kan tadi. Apa ni? AISI 1045 hot roll. So what is the SUT value? AISI 1045 hot roll.
38.
38.
Ni, nampak kan? Tuan ni appendix C2 kan? Plus. This one kan? 796. So will be SUT 638. Right? So SUT is 638. Why as well saya kena cari? Because just kalau dia tanya Langer, yeah, we use SY. Just catat je. SY is, his strength is 414. If the question asks about Langer, you need to find 638 megapascal, right? Okay. SN is berapa of ni? Guys, calculate untuk saya lah. 0.5 638 berapa? Berapa ni? 638 bagi 2 berapa kelas?
319.
Ah?
319.
319. Okay, 319 megapascal. SN dah. Load factor apa? What is load factor? How do you find SCL? You go back to your textbook, chapter 8. Mana table apa? What table is that? Cepat sikit. Page CL ni. table. Ini semua guys, you highlight this thing. Open book in your test 1. You gonna bring your book. Ataupun the printout. Kan ada extracted version. The one you bring, everything is there. Table 8.1. Okay, our case here, if you look on the question, mainly this thing, which one govern? Is it bending or it is bending, right, class? Tapi because I have not constructed the big, normally if you look 2 kilonewton, 0.3 kilonewton, and this very high, mainly for shaft is bending. But sometimes be careful. Sometimes the torsional stress is much bigger than the bending stress. You mean the torsional stress govern. In this case, most of the case is bending. That's why in this textbook, we go for column number bending. Understand that, class? Class, are you there? Bending. Okay. Normally for shaft, mainly. Tapi you got to be careful bending. Okay, for load factor for CL is 1. Class, are you there? CL is 1. Can you see this one? 1. Clear? CL is a load factor. All right. Class, are you listening or not? Boleh dengar, Right. CG is a gradient factor or size factor. So what is the diameter of the shaft, class? Diameter of the shaft berapa? Is given nak. Berapa diameter of the shaft? Okay, because we are shoulder and notch yang kita focus. We are taking the smaller diameter lah. We're not talking because if you look the question here, the bigger diameter is not critical because the shaft diameter is big. The critical is because shoulder we take the smaller diameter. Remember 40, or the right also 40, right? So we take the shaft diameter is 40. So it means the shaft diameter is 40. If you go for CG here, 40 is between 10 to 50. Betul class? Here is range from less than 10. If the shaft diameter is less than 10, it's 1 because we focus on bending. But because since the shaft diameter, the smaller one is diameter 40, so we will take, because 40 is between 10 to 50 is 0.9. So CG is 0.9. Clear? Boleh Plus?
Boleh.
Alright. CS. Okay. CS is surface factor. Okay. Is it stated the shaft? Dia cakap the shaft, what type of surface finish of the shaft? What is stated in the question? The shaft is made of AISI 104 hot roll and been machined. Can you see here? Been machined. It doesn't say polish. It doesn't say grind. Yang really, really smooth. It doesn't say polish like a mirror. No, not necessarily. Just lathe machine. When you do shaft and you lasing, machinery. Itu bukan polish. It is not grinding, just lasing. It said normally machine. But be careful. Sometimes question is do extra things. Sometimes it said the surface is fully ground, fully polished, something like that. But this is just machine. Surface finish of your shaft. So what we do to get CS figure 8.13. Figure 8.13 is here. Can you see figure 8.13? Ini also you highlight, you guys, in your textbook. So, okay, here we have a figure here. Based on, remember our SUT is 638. So SUT is your x-axis. So the y-axis your surface factor CS. So what is SUT here? No, do not take the upper scale. Upper scale is for English KSI, the bottom scale. SU, can SU is your SUT gigaparsec. 638 is what? 0.6. Betul tak, class? Class, are you listening or not? Class? Yes. SUT is 638, right? So 638, this is 0.7, middle, right? It is 0.65. 0.638 here lah. Saya punya garisan ni tak cantik, saya pakai tangan ni. You bring straight line here, up until the intersect apa? Sorry, ini not supposed to be crooked lagi because my mouse. Straight line up until here. Can you see the line machine? Can you see this line is machine? Do not take the second line apa? This is fine ground. Ini the polish one. This is mirror polish. Not necessarily unless your shaft like that. But normally shaft is machine. So you bring 0.638 here up until intersect with machine or cold draw ni, machine line. This is machine. So it will be 0. Apa ni? 0.78. Betul tak, kelas? That will be your surface factor. Okay. So that will be your surface vector. Then, okay, what about CT, temperature? CT apa? Temperature factor. If you look here, temperature factor, CT, temperature factor, kalau value is 1, because we always look at the bending, because the bending is governing. The shaft, not axial stress, not torsion. We look at the first column. Temperature normally is not given. Temperature is always less than 840 degrees. Unless your system is already mentioned in the question, is special, the surrounding condition is kind of like heavy duty machine. The temperature is increased. Maybe your part of your power transmission, your shaft is close to the furnace. It's kind of high temperature when during operation. You have to take using this question one, the second level. What is your factor? 1 minus. But in most of the case, temperature is less than 840. Even it's not mentioned here. Okay, he said the working temperature is 200 degrees Celsius. 200 degrees Celsius, of course, is less. What is 200 degrees Celsius in Fahrenheit? Berapa kelas? Celsius to Fahrenheit. Factor berapa? Kalau 200 berapa? 200, 3812. Is 3812 is higher than 840? No, can. So 1. Correct. Right? So CT is 1. Are you watching now? Okay. CT is 1. Okay. Reliability factor. Okay. Question say reliability berapa? The working temperature is okay. Temperature is 200. Okay. CT is 1. CR reliability factor is 90%. 90% here. 90% berapa? Class here 90%, right? Okay, 90% 0. So CR is 0.897. So you can straight away calculate SN. So you need to be clear. In test memang time limited. You need to be fast on this, right? Yang ni I show you a little bit slow. So your SN is 1. CL, CG is 0.9 times CS 0.78 times CT is 1, CR is 0.897 times your SN prime is 319. So that will be your endurance limit. So what is the value? Calculate. Berapa? Berapa kelas? Okay, in the solution it says 0.76. Tak apalah, saya punya tadi saya buat the graph CS tu quite 0.76 lah. Because I remember I do it by hand crooked to get the CS. 0.76 is more accurate. Because 0.9, nampak? 0.76. CR is 0.897. So when we calculate SN is 195.72 megapascal. Class, are you with me or not? Senyap je semua. Class, endurance limit.
Yes.
Yes.
Okay, first, then, okay, because the main thing we need to find here, right? SUT already know here, right? 68. Okay, now, sigma EA, sigma EM. Your bending, there is sigma EA, sigma. So what is sigma EA, sigma EM? So this equation. Remember this equation on page also, you must take note. Sigma EA is sigma amplitude square plus 3 tau E square. Sigma EM is sigma mean over 2 plus square root tau mean square, sigma mean square. Okay. But you cannot calculate, but unless, okay, you cannot calculate it if sigma, okay, you need to do the shear diagram. You need to do the shear diagram because to calculate the bending stress, you need M moment, right? Okay, if you look on this question, be careful. This question, they have 3 cases. We have axial stress. Along the shaft, we have P kilonewton. It means the shaft is kind of like in tension. This is not normal case. It means the shaft have tensile stress, have axial stress. And of course, based on 2 kilonewton, the pulley mounting in T1, T2, we have the shaft is in bending. And also because of between A and B, the shaft is in torsion. Torsional stress between A and B. But before O to A, before A, no torsional stress. After B to C, after B also, no torsional stress. It means between A and B. If you look here, A and B, tengok keras, if you look on this figure, because we have two conditions here. Because remember, as I mentioned to you about stress concentration factor. Okay, where is, okay, here, when you do, where is the, where do they mount? Okay, the pulley here, A. Can you see the pulley A here? Pulley A is here. Can you see the line middle here? Nampak tak ada 20 millimeter kan? Class, are you watching or not? Class?
Yes, doctor. Yes.
Okay, we have here, pulley is mounting at location at center here. But okay, when you do shear diagram, you will do shear diagram. This one I need to make it shortcut. You know how to find T1, T2. I remember previous example, T1 is 0.5 T2 because it is 2 kilonewton. Okay, this is the way the torque is like this. This is bigger, this is less, and this one supposed to be like this. Okay, so it means T1 is much bigger than T2. Ini salah ni. Ini salah ni. Guys, ini typo ni. T2 is 0.15 T1. Let me check the solution. I think that one is an error. T2 is 0.15. Yes. T1 is, yes, T2 is 0.15 T1, not T1. Any typo, no, this one, typo. T2 is 0, because T2 is lesser, because the torque is supposed to be like this, right? Okay. I believe this one you can solve it to do the shear diagram. That's why in the solution, if you look on the solution, they already construct the, okay, let me make this maximize. Okay, the solution, then they construct the shear diagram. I believe this one you can do because why? This one, we only have, okay, since the axis is just like this, okay, they didn't put the axis, but actually the axis is, okay, let's say this is X, right? X, and this is Y. Okay, this is Y. Okay, this is X axis. This is Y axis, and up is Z axis. So what plane our shear diagram? Do we have exact axis, that class? No, and everything is XY. Class, are you there? Class,
Yes,
are you
doctor.
listening or not? This is only on SY.
Doctor.
This is only on SY plane, because can you see the T1, T2 only pointed Y direction, and pulley A only pointed this direction. Okay, I want to make it sure because time very limited. I believe you guys can do this shear diagram, right? They already solved the shear diagram because this is on XY plane. This must be on XY plane because we only have one plane only. So reaction you can find it bearing at O, this is pulley at B, pulley at C, and bearing at D. This one, of course, you can, remember we already discussed this. You can make the shear diagram and you make the moment diagram. If you look, okay, carefully, there is moment diagram. Okay, they already make the moment diagram. The moment you nampak tak? Add here. This one, can you see the 293.25 Newton? Okay, this is times 2000 because the lecturer do the solution meter. Millimeter times 2000. 293.25 times 1000. Okay, this is much bigger. Actually, here they skip it. Actually, this one much lower because if this is this is negative side at shoulder here, at the at the right side of the shaft. This one here because we have a pulley B. Pulley B is here. This is okay. Yang this one pulley A location is here. Pulley here is here. 293. This is pulley. Can you see? This is the level of pulley A. 293. If you look the diagram, the shoulder is 20 millimeter shift to the right. The notch 20 millimeter to the left. If you look the shear diagram, nampak tak? We have M2, M notch. M2 is for the shoulder. Okay, this one, I don't need to explain to you. You can get this thing. If you know this 293, you know the distance here, all the distance based on the shaft length. You know the shaft dimension is already there, 250. So it means from here to here is 250. From here to here, from here to the level of pulley is 250, right? 250. And also to the B, because B also to 300. From here to here is 300. Okay. Okay, actually, the image shortcut, this one actually the value on the pulley B is much less, even negative, but the magnitude is less than this one is critical. It means we focus at on the left side. We focus at this, at pulley A. Okay, at pulley A that we focus, okay? Because since from the moment diagram, here is much greater value in magnitude, in terms of magnitude. Okay, 293. This one you can get it because this is, if you look here just now, 250, right? 250. So it means 250. So it means here is 250. Here is 250. From here to here is 250. Here is 250. Okay, 250. So here kan dia jarak dia kan 20. From here to here is 20. From the notch also jarak dia 20. So theorem Pythagoras, I don't need to explain guys, time very limited. You can get this M2. Kalau you tak tahu get M2, M1, problem. Mathematics you very poor. Theorem Pythagoras, you can get this. This one over this one over the distance. You can get this both two value at the notch of the groove and also the shoulder. Okay. That's why we have two cases. Okay, because we are not focusing even at the pulley. Location pulley is at the center where the value moment is 293, but that is not critical actually because at the pulley, if you look, if I zoom in, pulley level is here. Okay, let me erase this again. You don't understand. Okay, let me erase back this thing. Pulley level is here. This is your pulley level. Pulley level is here, not at the notch. Pulley level where you know moment already given on the shear diagram tadi. Shear diagram tadi 293.25. Pulley is here 293, but you can get here the shoulder by theorem Pythagoras. You can get it. Ini you can get it. Mathematics, basic mathematics. And two. Okay, this pulley here, but shoulder is here. Shoulder where we have a notch. Here the shoulder. Here is the shoulder. Nampak tak? Shoulder. Okay, let me go back to your live video. Okay, it means, okay, if you look at my live video, tengok sini kelas. My live video, okay, sekarang ni, the shoulder. Okay, this is the shoulder. Let me make it bigger. Okay, ini diameter. D is 60. And we have a smaller diameter. D is, okay, because the shoulder, okay, the shoulder. Okay, it's stated that all the fillet, all corners are filleted, R is 20. It means this shoulder we have fillet radius. We have a notch radius. R is 2. Okay, the smaller diameter ni, the D here, the here is 40. Smaller D is 40, bigger D is 60, and the notch radius is ni. So we need to find, because from the moment diagram, okay, from the moment diagram, okay, if I zoom in, moment diagram is like this, right? We have like this. The critical is where we location because A is where we mount the pulley. But this is shifted another 20 here. Okay, you know already because moment at A here is where the pulley we mount. And the value is 293.25 Newton meter times 1000 Newton millimeter, right? Here we can get it from theorem Pythagoras. We can get it because we know the value here is 20. You know, you can get this value. It is M at shoulder. Shoulder is 270.17 Newton meter. Okay, we focus dulu at shoulder. Class, are you listening? Class, cepat sikit. Saya nak cepat sikit. Class, kita 2 hours. Class, are you listening or not?
Yes, doctor. Yes.
Right. We are, because shoulder we need to get satu shoulder, nothing later on kita go for the groove also. These two things, not at the plane where the pulley is mounted here, but here is where we have a ni. Kalau when we have a notch, itu ada stress concentration better. Even the moment is lower, but not as big as at where the pulley A. Where pulley A we don't have any notch. At pulley A where we mount the pulley, just a plain diameter, but little bit 20 millimeter to the right. We have a shoulder, that one we have a notch, we have a fillet. That one will cause stress concentration. So what is the value of moment at that point is already a theorem Pythagoras based on your moment diagram. So this value that you need to take for your bending stress. Okay, the bending stress at the shoulder. Okay, tengok bending stress at the shoulder. Tengok sini. I need you to focus. Bending stress at the shoulder. Okay, at shoulder. You kena tulis like this. At shoulder. Okay, bending stress apa? Bending stress is 32 moment at the shoulder. Remember this one, at the shoulder, not at the pulley, the shoulder, you can get it from theorem better. You can get it, okay? At the shoulder over, because it is shaft, pi d cube. Okay. Which diameter, sir? Take the diameter of the smallest one. What for? We take the maximum one, because maximum is not critical. Because critical is the minimum diameter. So this diameter, is, so we have 32 times moment from here at shoulder 270.17. 270.17 ini I times 10 to the power of 3 because this is Newton meter. Newton millimeter times 1000, right? Over pi over diameter. Which diameter? The smaller diameter, 40 cube. So this will be the value in megapascal. The answer is shoulder is, dia dah calculate, mana dia? Dia dah calculate. Or you can calculate for me. Mana? Mana dia calculate the bending stress? Ni. Ini okay. Mula dia focus at the, if you look here, dia focus at the shoulder. At the shoulder, the bending stress. Ni. Dia tu ada kena kali dengan KF. Nampak? Dia kali KF. 32 moment. Okay. Dia already calculate. It's not showing here. Because dia dah, this one dia use the mascat. Dia already substitute. Dia kali, mas kali. 32 moment pi d cube. Okay. So this is a value. So this is the value. Okay, berapa guys? Can you calculate for me 32,27017 times ni? Ini because I already convert this in Newton millimeter.
43.
143.
43. Oh no, just 43 megapascals.
143 megapascal. Okay, thank you. Okay, this is 143 megapascal, right?
Sorry, total 43. 43.
43.
43 saja kan? Baiklah, Mat, bukan 143 kali dia. That's why kita dapat dah kali dia dari 78.26 kan. Okay, 43 only megapascal. Okay, need to multiply KF because we are at shoulder. Remember, at shoulder we have stress concentration factor, but we are dealing with fatigue stress. Fatigue stress concentration factor. Equation here. Fatigue stress, because this is bending. This is bending. Okay. Bending. Bending, we have sigma bending. Sigma, okay, KF bending. Fatigue stress for bending case equal to 1 plus Q is the notch sensitivity based on bending. Based on bending times KT bending. Okay, this is static stress concentration factor based on bending minus 1. So you need to find this first. You need to find the KTB first, QB and KTB. Then you get the fatigue stress bending. Fatigue stress bending that you calculate will multiply by your pure bending, your raw bending. It means your bending stress, you take the stress, you take the maximum case where you have a notch, where it will be more elongated compared than pure like this. Pure is like this, normal, but you have notch, you need to multiply. So mean this sigma B, your sigma bending is KF bending. KF bending times your KF bending times your 43, your sigma bending yang nominal, yang before this. I think this one is nominal, yang we not multiply. So you need to, your sigma bending must multiply by KF bending. So how do you find the fatigue stress bending? Fatigue stress concentration bending, 1 plus Q bending, KT bending minus 1. So that's the equation. I stated already here. KF bending, fatigue stress is KF. Okay, to make not confused, to make you not confused like this. Okay, let's say to put equation like this. KF, okay, KF, fatigue stress concentration factor is 1 plus Q KT minus 1. But it depends on bending, torsion, how it looks like. And okay, how to get KT bending? Okay, KT bending, okay. KT bending, static stress concentration based on bending. If you look on your textbook, okay, in chapter 4, okay, in chapter 4, hold on, chapter 4, static stress. Ini you can take note, this figure, if you look at this figure, static stress concentration factor on chapter 4, based on static, on figure This one, okay? Take note, Okay. Start from here. Static stress, chapter 4, static stress concentration factor, KT. Okay, if you look here, we have three categories. This is step shaft, kan? We are dealing shoulder, step shaft, kan? This is shoulder. The first part is shoulder, figure 5. But the second graph here is based on notch, groove. Remember, we have a groove on the left. This is based on the groove. Okay, this one is on, we have holes. Only rarely we have holes on drill through the shaft. But our case, we focus on this is bending because at shoulder, this is shoulder, right? Shoulder, okay, shoulder, the part A is for, part A is for, can you see the moment, this is for bending, okay? This is bending, this is for bending. Okay, B-E-N-D, this is for bending. Okay, this is for bending. The second, this is axial stress, this is for axial stress. This one is for torsional stress. So it means we have to, in our case, okay, for bending, we need to multiply by, okay, see how do we get, because KF is 1 plus Q, KT minus 1. KT2 will depend on station. Bending for bending. All right? Bending for bending. Okay, KT bending, since we go for bending, right? Okay. Can you see the graph here? Guys, are you listening? D is plot, if you look the distribution on the graph, D is D over D. D over D. What is D over D? It means the bigger diameter over the smaller diameter. Because if you see in this, if you look on this question, the bigger diameter is, our bigger diameter is 60, right? D is 60. Our D is 40. And our notch radius, can you see the notch radius is R? R is 2 millimeter. Okay, that's why we use just now. Okay, R, smaller d, bigger d. So D over D is what? Our bigger D, so D over D over 60 over 40, right? So if you look on this distribution, can you see can you see we have a line, a lot of line here. So this is based on the ratio of D over D. 60 over 40 berapa kelas? Kelas 60 over 40 apa?
1.2.
1.5. 1.25 kan?
No, 1.5.
Oh, sorry. Tak saya. 1.5 kan? Okay. 1.5. 60 over 40 is 1.5. So where is 1.5? Nampak tak? Kena zoom betul-betul kalau you nampak sikit. Where is 1.5? 1.5 mana? The first one is 6 kan? The second is 3. Number 3, betul? Can you see number 3? This is the line of 1.5 ratio of D over D. The third line, the third curve. Okay. But the x-axis is R over D. So what is R? So in the question, R is 2 millimeter, right? The fillet radius is 2 millimeter, as I show you in my image here. R is 2. Bigger D is 60, smaller D is 40. Okay, ratio D over D 1.5. R over D, 2 over 40. What is 2 over 40? 2 over 40 berapa ratio? R over D berapa? 2 over smaller D. Berapa kelas?
0.05.
0.05. So if you look on the graph, R over D, so the x-axis is R over D. 0.05 is here. Nampak tak? This is 0.1, 0.05. So you bring this up. So this is 0.05. Bring this up until it intersect the third line, because the third line is 1.5. So what is you bring there? The left is your KT value. So what should be your KT for bending? KT bending berapa? KT untuk because we are bending. KT bending is 1, berapa tu? 2.1, right? Third class. Here. Ni kan 2.1, this is 2, 2.2, 2.1. Sorry, this is 2.0, 2.1. So it will be what? Close to 2, betul right class?
0.04.
2.0. Don't have to be that precise lah. It's okay. Kalau you precise lagi cantik ya. 2.04. If you look on the solution, what the value of the KT bending? KT bending is 2.02. Okay lah, 2.02. Right, 2.02. So it is 2.02. Okay, that's how you get it. Pump that class to get the KT bending. 2.02. That's a solution. They have this 2.02. Okay, that one's for KT. KT, okay. But equation KF fatigue stress 1 plus Q. KT we already got it, but Q is the notch sensitivity. Notch sensitivity you get it from Notch sensitivity is you get it from your textbook also. Okay, your notch sensitivity is from your chapter 8. Chapter 8, if I zoom in, chapter 8, notch sensitivity is chapter 8, fatigue stress. We have graph on notch sensitivity, not this one. That one for CS, notch sensitivity is, hold on, chapter 8, fatigue stress, notch sensitivity is here. Ini also you kena take note. Ini chapter back, go back to chapter 8, fatigue. This is notch sensitivity. Ini pun you kena take note. Figure 8.24. Okay. It said that notch, our shoulder, the radius of fillet is apa tadi? 2 millimeter, right? So we use the x-axis here. Now, can you see the x-axis? Kalau not, the upper one is English, bottom one. So 2 millimeter. Bring it up, bring it up, bring it up until it intersect with the, can you see? Okay, this is all the distribution of the scale in terms of, okay, use this value. You have two zones here. You use this scale from 50, 60, 9, 80, 100, 140 to 200 for bending and axial. You use the second zone scale for torsion. But in our case, bending, right? We are focus bending, we use this scale on the left here. Okay, what is this 200? 200 is SUT. Faham tak kelas? This 200 is the SU. What is this 200? 200 KSI. Okay, 200 KSI means, okay, since in our case just now, our SUT that we found out is apa tadi? 638 megapascal. It's not KSI kan? Actually, you can get the table tadi kan? You can get the table tadi pasal this graph dia plotted by American engineers, ASME. Okay, American engineer, they already done it. Because American, they practice English unit. They conducted the test. All the data is English. You just convert to KSI. Understand, class? To get the what your value of your SUT to 200. No need to convert ataupun you go back to appendix. Ni page berapa tadi? 309. Okay, I need to 309. Okay, now. Okay, this page 33. Yes. Apa page tadi? Page 337 on my PDF 337. Okay, appendix C. Then just now we go for appendix C. Jadi AISI. Remember AI? So how do you get this thing? This is 638. KSI dia berapa? 92.5. Class, are you there? Class. This. Just take this one to get your value of Q because apa page saya tadi? 337. Go back to this one. Yang ni. Apa value dia tadi? Saya lupa. 390 apa tadi? Berapa value saya tadi? Okay, 92.5 kan? Your SUT is 92.5. Go back yang tadi, 337. You graph ni balik. Okay, 92.5 KSI. Where is it? Nampak tak guys? We are using zone, this zone. Because it is based on bending. Class, are you listening or not? Class, are you with me or not?
Yes.
Okay. SUT 92.5. Nampak tak? This is 200 KSI. This is 140. This is 100. This is 80 line, 60 curve, 50 curve. Which one that close to 92.5? 100, right? And this value. No, we are not using in bracket. Bracket is hardness. You can use hardness also. Hardness is as I explained to you. Hardness ada. You can convert to, but this one is here. Here is KSI value. 92.5 is 100, right? Close to 100, somewhere close to 100. So your line curve, you pakai pencil. Now, you sketch your pencil, bring your pencil. This is the line close to 100, 92.5. Here, there will be your curve. You intersect with radius, since the radius of the shoulder is to intersect. Then, so what you got the value on Y? 0.8, kind like 0.8. Betul tak? So your Q here is 0.8. So that's why you punya Q sini is Q is 0.8. I hope you understand class what I'm explaining to you because masa berjalan ni saya nak kena cepat. So that is 0.8. So you calculate that. So what is your KF? KF bending equal to 1 plus 0.8 because Q is means notch sensitivity. Okay, this is about notch sensitivity. Notch sensitivity. They have a kind of this equation. So put into the 1 plus Q in bracket KTB. Since KTB is 2.02 minus 1 times 0.8 plus 1. So you got your KFB is, so you have your KF based on bending. Ni ada based on bending. KF is 1.82. Betul tak? Am I doing right? Q is 0.8. Betul kan? Class solution. Can you see the sensitivity 0.8, right? Here. Class, are you with me or not? Class 0.8. Betul?
Yes, betul.
Nah, ini BSN pun boleh dia pakai BSN. Tadi I straight away yang tadi 93.5 SUT pun boleh lah. Yang ni. Okay. So you got your K. So since KF bending 1 plus Q KT minus 1. So you got KF 1.82. Okay. Tengok sini. This KF 1.8 can that one multiply with you punya bending. KF bending kena multiply. Kena times this. And then because this bending stress, because you have at notch at the shoulder, that one you are the multiplication because they extended your stress distribution much longer. Because at that notch we have more stress constant elongate. The stress concentration much greater compared with without notch, just a plain diameter. Be careful, so that's why we need to multiply. So sigma bending is KF kali sigma bending O. O means nominal without multiplication. The first one. So we need to multiply. So it means 1.82 times 43 megapascal. Remember sigma bending we calculate just now is at the shoulder punya moment 43 megapascal. That's why we got sigma bending is, so our sigma bending now our sigma bending is after we multiply we got 78.26 megapascal. Okay, paham okay, I hope you understand. This is bending dulu. This is bending, okay. We have 78.26 megapascal, okay. This is bending. Okay, guys. Kalau in this case the shaft is rotating, kalau we plot, okay. This before I go to this. Okay, this is bending. Before I go to this, because we need to find sigma EA and sigma EM. This is on the sigma bending. Kita belum lagi masuk torsion at shoulder juga. Torsion at shoulder. Okay, if you look back, this one, if you look back at this still shoulder, kalau you tengok torsion happen, tengok class, are you listening or not? At shoulder we have torsion or what? Remember, between A and B ada torsion. Before A, no torsion. After B, no torsion. A is torsion between A and B. At shoulder is here, right? A is here, B is here. Is shoulder between A or B or not? I'm asking you guys. Shoulder here, okay, remember we focus on now for torsion. Do we have torsion at shoulder? It's within A and B, right?
Yes.
Yes, we have torsion at A and B. So we have torsion. That's why we need to focus on torsion, because what is torsion? Torsion, you can get it. So what is torsion actually? Okay, now for at shoulder, because we are still focused at shoulder, guys. Now we go just now bending, now torsion. So what is the value of torsion? Torsion is because we need to find the torsional stress, the either 16T over pi d cube. Okay, torsional stress, we don't take the bigger diameter 16. No, we're taking the smaller diameter. That D is 40. We need to find the torque. Since solid shaft, and this equation T, the torque. What is the torque? The torque is here 0.2 kilonewton because the diameter of the pulley A is 200. So what is torsion? Torque is 2000 Newton times the radius times 100 because diameter is 100 minus 0.3 kilonewton, 0.3 times 100. So that will be the total torque. So you got the total torque value. If you look here, the total torque is already calculated. Above here, if you look here, the above, the torque is 170. Torque is 170 times 10 to the power of 3. Okay, Newton millimeter. This torque, we already have a torque. So we have a torsional stress, we put the value there. So, but this torsional stress at shoulder, Because at shoulder A to the right of shoulder at just now shoulder is to the right of pulley A, right? So we need to find the torsional stress. Tadi moment bending, torsional stress. So torsional stress, okay, we know torsional stress. So torsional stress yang pure. Torsional stress yang pure here is okay, this one you calculate already have. We have a value there again. So is torsional is 16 times 170 times 10 to the power of 3. This is Newton millimeter over pi. Diameter, smaller diameter is 40 to the power 3. So this will be your value in megapascal. Can someone calculate it for me, please? Cepat sikit, kelas boleh tak? Ini susah kelas online ni. Boleh calculate untuk saya ni? Kelas
13.53.
13 eh?
Yeah,
13.53 megapascal. This is TOO. TOO mean raw, torsion, raw. We not multiply yet by fatigue stress, torsional stress, fatigue stress concentration factor based on torsion case. So this TO mean raw. Raw at shoulder we have torsional stress also, but this is raw, not yet multiplied by fatigue stress concentration factor based on torsion. So what is fatigue stress concentration factor based on torsion? KFTS, I put it like this, torsion. Fatigue stress is 1 plus notch sensitivity Q based on torsion, bracket KT based on torsion minus 1. All right? Because we are focusing at shoulder. Okay, shoulder diameter bigger 60, smaller diameter 40, notch radius is 2, and notch radius is 2. So we go back, okay, tengok sini, we go back to the, if you look in your textbook, we go back to chapter 4 tadi. Okay, we go back to chapter 4. We go back to chapter 4 tadi, sepatut saya mark no, page number, saya dah lupa. Page number tadi apa? 337. Page number, go back to chapter 4, stress concentration factor tadi just now for shoulder. Tadi we go for bending, now we go for, hold on, mana tadi? This one. All right, okay, if you go here, okay, this one we go for bending. Now for, this is axial. Now, do not take this one. Ini is groove. This is groove. We are talking for shoulder. This is axial. The third one, shoulder torsional stress. Can you see that? Torsional stress at shoulder. Okay, in this case, KT. Okay, since our D over D tadi just now berapa? D over D. Okay, D is a ratio. D over D is 1.5, right? D is 60. The smaller D is 40. D over D is 1.5. And R over D is 0.05. Okay, you use this one. Do not use yang bending. You get the wrong KT. This one to find the KT. So R over D is apa tadi? 0.05 is here. 0.05 until intersect 1.5. Nampak tak? Ini 1.2, D is 2. So about around here lah kan? Somewhere you have you sketch with pencil lah this line. Betul tak kelas? Somewhere there. Class, are you listening or not? You punya curve. Because this is 2, this is 1.2. So you have to sketch by pencil. You punya this curve of 1.5 because D over D, our case is 1.5 is between 2 and 1.2. So you sketch kind of like a curve follow the flow. Kind of like this. You sketch like this. Jadi is 0.05 R over D. You intersect, you got ni berapa ni? 1.6. Kalau you accurate lagi cantik lah. Jangan just roughly, quite accurate you need to guys. Jangan cakap ni you take it 1.7, no lah. I don't think so. This is 1.68. Betul tak? This is 1.68. So this KTS, the torsion is 1.68. Kalau you tengok torsion TS 1.66. Okey lah, 1.66. Dia buat 1.66. Itu tak salah student, tapi jangan lari banyak. 1.66. Okay. Okay, what about how do you find the Q? Macam ni define the Q. Okay, page 337 balik 337 notch sensitivity. Go back to chapter 8. Okay, this is just now for bending. Okay, just now for bending. Sekarang KQ, notch sensitivity based on torsion. Remember you said use this value. You use the right zone, the right scale, not the left. Just now left scale for bending and axial loading, but this one based on torsion because we are torsional stress. So use this scale on the right one here. This use value was torsion. Okay, remember that our this is value of our SUT in KSI, right? Remember 938 is now our SUT is 638. Remember from table is 93.5. Betul lah kelas? Tadi kan? 92.5. So S this is 180, this is 120, this is 80. So somewhere here lah the curve 90. 90 is somewhere like this. Okay, and our notch tadi is radius is 2, right? 2 millimeter. 2 millimeter. Radius is 2 is here. 2 millimeter up until it intersect. Kita tadi 93.5 KSI. Okay, so this is 180, 93, kind like this. So you draw a curve, follow the flow of this curve, kind like that. So between 0.8. Can you see that this is 0.8, this is 0.9 and on your y-axis is kind like 0.86. Cuba tengok Solution, yeah. Based on torsional 0.86. Itulah. So you punya QTS is 0.86. Right? So that's how you find K, fatigue stress, concentration factor based on torsion. 1 plus 0.86 times our KT torsion tadi is 1.66 minus 1. So that's we got KF torsion is 1.57. KF based on torsion is 1.57. Class, are you listening or not? Class, are you watching my video class?
Yes.
Right. So that's why knee fatigue, this is fatigue stress concentration factor based on torsion. Then you kena kali dengan raw torsion 13.53 megapascal. So you punya torsional stress, ini semua cerita shoulder, belum notch lagi. So you understand what I'm talking about. Ini baru shoulder. Torsional stress is KF torsion times you punya torsional stress yang raw just now. Raw we calculate 30.53. So our KFTS 1.57. So we got the value in your solution is yang ni. Nampak tak? 121.24 megapascal. Megapascal already calculated for you. 21.24 megapascal. Itu torsional stress. Alright? Tengok sini Memang panjang cerita ni guys. Ini this why just do not worry lah. In test 1 not this too much. Ini kalau you faham this thing, test 2, question 2 no problem. This is assignment discussed in class. Faham tak class? Are you listening class? For exam not this long lah. I hope kalau you understand what I'm talking about. But sometimes when you look at the solution you don't understand. I hope by explaining you understand what is the solution. Try to explain to you. Okay, torsional stress kena multiply by fatigue stress concentration torsional stress. The procedure ni see my video I already recorded. I forward to you. Okay, torsional stress kali fatigue stress. Okay, one more thing belum habis lagi. Look at dia. Dia cakap also stated that we have axial stress. Nampak tak? Along OABC we have P2 kilonewton. Can you see that one? We have axial stress. It means either OABC, they have axial stress along the shaft. Torsional stress only happen between A and B. Be careful on the notch. Be careful. Nanti you kena focus on the notch at the groove. Sorry, groove on the left. Left here. Nanti you kena focus juga on the left the groove. The groove here they don't have torsional stress, but they have the bending stress. The bending stress is on the yang tadi tu. The bending stress is at the yang ini. This value. Tadi kita sekarang ni we still lagi on shoulder, tapi yang tadi on the groove tadi on the left ni you use bending stress M1 because it is a groove position of the measurement. But where we are still tadi bending stress we are talking on the right at the shoulder. We are not talking about the groove. The shoulder we already done the bending time the KF bending The torsional stress already at the, because torsional stress, we have it, right? We have it on the shoulder because, sorry, on the shoulder, we have torsional stress also. But number 3, axial stress, yes, we have. And any case, any point, shoulder or groove, we have axial stress. Okay, axial stress, look at my live video, right? Axial stress, we have, okay, you mean at shoulder, we have 3 cases. Axial stress. Axial stress, what is the basic equation of axial stress? Class, sima axial apa? For solid shaft. For shear berapa? 4F, actually force over cross section, but shortcut formula 4F over pi d square. Class, are you listening or not, class? Kan? Axial stress. Okay? Axial stress. So, what is the force? What is the force? Force apa, class? Is given here. What is the force? 2 kilonewton. Class, are you listening or not? 4 times 2000 Newton. Class, are you there? Pi.
Yes, yes, doctor.
D bawah apa? What is D? Small d apa? Diameter. Which diameter? 60 or 40? Worst case apa? Bigger diameter or smaller diameter? Now it's axial stress. Tadi torsional we already done times the FTS. 40 or 60?
40.
Kan? We have shaft like this, can? We have shaft like this. We have shaft. Along the shaft, okay, we have shaft step like this. This is 60. This one is 40. This one is 60. Along ni we have axial stress, right? Axial stress. Axial stress. You know axial stress, kan? Axial stress. Force over cross section area. We taking the smaller diameter or bigger diameter? At shoulder. Shoulder here. Which one the worst? Yeah, smaller diameter. Okay, that's my question. Okay, smaller diameter. So 40 square. Okay, 40 square. So axial stress jadi berapa ni kelas? Berapa axial stress? Yang ni solution dia tak tunjuk. Solution dia tak tunjuk this one kelas. Dia only dia shortcut saja. Nanti kalau you look through solution, you not that quite understand. Maybe through my video axial load. Okay, axial load berapa? Ni dia dah kali KF terus. Before that, the raw, sigma axial raw, sigma axial raw, without multiply the fatigue stress concentration factor based on axial loading. Berapa ni?
1.59.
1.59
59.
megapascal kan?
Yeah.
Megapascal, baru raw, belum. Need, this one also, axial stress, you need to multiply KF, fatigue stress concentration, because we are talking about shoulder. We have a notch, D over D, R over D. So we need to find the KF. KF untuk axial, KF untuk tengok look at my live video. KF untuk axial case equal to 1 plus Q notch sensitivity based on axial in bracket KT axial minus 1. Alright. KT axial. Okay, go back to KT axial. Kenapa kau tak remind saya page berapa tadi? Saya pun nak pergi balik. Page berapa tadi? Textbook. Chapter 4 tadi. Nanti korang highlight your textbook. Textbook tu korang highlightkan bookmark. Understand me? You know where to go nanti, especially for your test one. Page berapa tadi? Page
149, page 149.
49. Thank you. 149 batal balik. Ya benar. Page berapa tu? Exact page in the PDF berapa? You boleh mark you tahu kan how to tak. In your hard copy textbook, you need to bookmark lah, easy for you to find. But digital, macam mana kita buat, kita boleh buat. Saya tak faham sangat cara digital to bookmark. Mana tadi page berapa? Here. Shoulder, the second one. Are you watching class? Here. Axial. Tadi kita use torsion. Tadi the first one, bending. Second, torsion. Now, this middle, axial. Use this graph for axial. Okay. D over D tadi berapa? Bigger D. 60 over 40. 1.5. R over D, 0. R over D, 0.05. Okay, R over D, 0.05. D over D, 1.5. Mana dia? Kelas. Which one 1.5? Nampak tak? The second curve kan? The first one is 2. Second curve is 1.5. 1.5 then you intersect. Jadi ni 2 point berapa ni? 2.1 kan? Nampak tak kelas? Are you watching? 2.1. So yang ni, ini KT, yang ni bukan band ni. KT. Axial is 2.1. Kan? 2.1 Alright. What about the Q? No sensitivity 337. Okay, 337. Okay. Axial kita pakai apa? Okay, axial. Tadi notch is 2. Okay, notch is 2. This line 2 mm because shoulder. Naik sampai mana ni? Tengok. Mana kita nak intersect? Which one? Kelas. Remember, use this bending. Use scale on the left zone for bending and axial. The right scale for torsion. Itu intersect with what? Cepat sikit. Tadi berapa? This is all KSI. Berapa tadi? Kita convert 638 SUT to KSI berapa tadi? Saya malah pergi pada appendix tadi balik. Berapa? 93 point berapa tadi? Close to 100 kan? This is because the third line here, this is 100 KSI. This is 93.8 KSI is between 80 to 100. Nampak? It's somewhere you make a sketch of your pencil somewhere around here. Somewhere here. Understand tak? Class, do you understand what I'm talking about, class? 93.8 kan tadi. Convertkan 638. Tadi our 638 megapascal. Convert to KSI is 93.8. Lebih kurang macam ni lah. You sketch a pencil. Curve dia macam ni lah. You don't have to ni lah. You don't have to sketch like me. You sketch here saja. Saya pun kalau you punya IQ lagi tinggi, you sketch kat sini saja Tapi flow dia sama lah. Betul tak kelas? Jadi somewhere is 0.8 lah kan? Betul tak? Q is Q axial 0.8. Betul tak? Clear? Tengok solution. Q axial. Betul lah cakap. KT dia. Kenapa dia KT 2.38 ni? Cuba kalau if you are watching. Just now I said is 2.1 kan? Why is KT axial 2.38? Do I make any mistake, class?
Yes, sir. I think you make the wrong line intersect. Should be the line above.
Okay, what is the page number again yang chapter 4 tadi?
149. 149.
149.
Yes.
149 pergi sini. Tadi page number ni. Tadi I make a mistake on finding the. Apa sah? Apa silap saya?
Garis tu kena naik sikit.
R over D 0.05, betul kan? Okay.
Ya. Kena sampai 1.5. Itu Bangkok punya.
Lepas tu?
Naik lagi. Sebab ni line 1.2 mah.
D over D kita is 1.5 kan?
Ya.
60 to 40.
Kena.
Apa one more?
Ya. I think this is the third line. Itulah, jangan silly mistake lah ni. Bentar. 1.5 ni the second line kan? The second curve. Okay. My mistake. Itulah, jangan make a silly mistake lah. Jadi 2.38 lah kan? Lebih kurang lah. 2.38. Alright? 2.38. Okay? 2.38. So this one is 2.38. So you put so your KF axial you put into equation is you get KF is 2.104 lah. So ini this is your fatigue stress concentration factor based on axial. So you punya sigma axial is KF times sigma axial nominal yang pure one tadi 1.59. So 2.104 times 1.59, so you got itulah 3 kan dapat ni. Ni yang dia tulis ni 3.35. Kelas, ayo boleh tak little bit I extend kelas Ni dah 4:11, boleh tak kelas? Is it okay? Kelas, little bit, another 10 more minutes, boleh? Kelas.
Boleh.
Boleh. Okay, sikit sorry Okay, 3.35. Okay. 3.35. So this is your sigma axial. Okay, tengok Kenapa sigma axial dia mean? Nampak tak? Why is torsion dia mean? Nampak M? They put it mean. Why the bending alternate? Kenapa? Remember. Alright. When you got all these values just now, when you got all these values, tau is mean. Because torsional stress along the shaft, if you look, the shaft is rotating. We have torsional stress at the shoulder is after A. Along the circumference of the shaft of smaller diameter D40 is remain. If you look at my live video, torsional stress versus time straight. Betul tak kelas? Torsional stress because torsional stress is along the circumference, whatever version type, it remain constant. It's not fluctuating. Straight. So torsion only have mean aja. They don't have alternate is kosong, 0. Okay, what about axial? Sigma axial, not bending, axial through times. Along the shaft, can you see? This is your shaft. Along the shaft, we have a constant axial stress that we calculate just now. Just now we calculate times axial loading with time is 3.35 times the fatigue stress concentration factor. It means we have 3.35 megapascal along the shaft through times, constant, 2 kilonewton. 2 kilonewton is not fluctuating, axial stress naming constant. So sigma axial versus time, straight line, constant, long time. So sigma axial only have mean. We don't have sigma alternate for axial is 0. You understand that, guys? Paham tak? We have mean. Torsion also we have mean, purata. We don't have alternate. Alternate sine wave, that one alternate. We don't have any fluctuating, you mean alternate is 0. Axial also alternate 0. But unless bending, except bending. Bending why? Bending, sigma bending. Remember as I told you, if you look here, because the shaft is rotating. Okay, this is your bigger shoulder kan. So, okay, kita kat sini, shoulder dekat ini. The shaft, because can you see the bending? Okay, this is your smaller diameter D. Okay, this is the shoulder that you focus, your element. Because the shaft is rotating. At the top, it is facing either, okay, let's say tension. When it goes down, it facing, when the shaft, the quadrant goes down, at the bottom quadrant, it goes to compression, then it goes to tension, it goes to compression, tension, compression, tension, compression. Now, it kind of like fluctuating. Clear that class? You understand me or not? Bending, yes. They have compression tension because the element is go up, down, and down while the shaft is rotating. Clear? Clear or not? Class, are you there?
Yes, doctor.
So you mean bending versus time, but bending versus time, they're not go positive, they're complete reverse. When it goes to tension, it goes to value of tension stress. When it go to bottom, compression stress, same value, same like that. For bending versus time, is like this. So they have their mean is 0, but they have sigma A. So the one that we calculate sigma bending from the beginning times kf bending, right? That is only alternate. They have alternate. So they have sigma A. That's why in the solution, you look on the bending sigma A. Can you see bending sigma A? Torsion only sigma mean. And also axial sigma mean. Okay, remember this equation. Okay, then we need, remember, in your textbook, also in this solution, you can find it under chapter 8. Let's go for page 338. When you go back here, this equation, you can take note on this equation where you have this one, when you have sigma EA, formula for sigma EA and sigma EM. Where is it? This one, table 8.2, also in this solution, sigma EA. That's why you need to find sigma EA because this is distortion. We need to combine sigma and tau. Sigma EA, guys, if you're watching, equation, the basic is square root sigma alternate square plus 3 alternate square. Okay, in our case, take note here. In our case, sigma A, which one that we have alternate? Which one that we have alternate? Now, are you watching class? Axial, we have alternate. No. Sigma axial, we don't have. But bending, we have alternate. Just now, we already calculate times KF bending. That's sigma alternate. So this one, we have, yes, we have. When we substitute, we have sigma bending square plus, okay, torsional, do we have alternate? We have torsional alternate. Class. In both cases, pasal torsional remain. No. Torsional 0. Torsional. Because this torsional stress, tau torsional stress. No, this one is 0. So sigma EA equivalent alternate is sigma bending square. Sigma bending, sorry, because it is square root. It's sigma bending that we calculate. So just now we collect our solution just now. Sigma bending from the beginning tadi times the KF bending. Be careful, sigma bending times the KF bending. This one, 78. The sigma bending itself times the KF bending, 78.26 megapascal. Okay, now the equation, back to equation just now. Okay, now sigma EM, sigma equivalent mean, equal to, this equation you must take note. Sigma mean over 2 plus square root tau mean square plus bracket sigma mean over 2 bracket square. So this is sigma EM. Okay, which axis? Okay, focus on just now bending stress. Bending stress, we have mean.
No.
No, 0. Okay, be careful. Okay, bending stress 0, but I cannot put this 0. What about axial? Right? What about axial? Just to check. Sorry, what about axial? Axial, do we have mean?
Yes.
Yes. So this is sigma axial. Clear tak, class? Clear tak? This one for sigma, right? Axial is also sigma bending, but this is sigma axial over 2. Clear tak, class? Axial, yes, axial we have mean, but it remain constant. Sigma axial remain constant, but they don't have alternate. Okay, this is sigma axial plus square root. Okay, tau mean. Do we have tau mean? Tau mean ada tak? Yes, we have tau mean. Yes, tau mean is tau. Yeah, tau mean. We have tau mean. Yeah, torsional stress with time KF torsional stress. That's tau mean. We have it. Right. Tau mean we have it plus. Okay, sigma mean. Do we have sigma mean? Sigma mean sigma apa?
Sigma
Axial ada mean. Sigma axial ada mean, right? Sigma bending, sigma mean is 0, right? But axial we have mean. Clear tak, class? Axial we have mean. Axial kan the mean, but alternate is 0. But yes, we have sigma axial. Are you watching my live video? Boleh nampak kan? Class. Sigma axial over 2 square. Clear tak, class? That's how we substitute. Nampak tak? Bukan, be careful about this. Sigma E mean is sigma mean. Sigma mean because axial stress remain time, they already only have mean saja. They don't have alternate. Okay, we have this. So we substitute sigma axial. And tau mean, yes, of course, torsional stress remain torsional stress. This one all stress here multiplied by the fatigue stress. KF bending for bending, torsion, KF torsion. Understand? We already multiply. This one also sigma axial. Nampak? In this case, apa yang replace for sigma bending only on sigma EA. Betul tak, kelas? Bending only on sigma EA saja. But torsional, they don't have alternate, right? So it means sigma EM, we have sigma axial over 2. So remember sigma axial just now that we calculate. Sigma axial just now is, sigma axial is mean, kan? This is sigma mean, sigma axial is 3, okay? 3.35 megapascal over 2 plus square root. Tau mean just now, we already calculate tau mean just now. Torsional, ini already must multiply KFTS, 21, ini square, sorry, 21.24 square plus, okay, sigma axial. Sigma mean over 2 square. Sigma mean only sigma axial that we have. So 3.35 over 2 square. Understand that, class? That's how you do it, you put into this equation. So that's why then you get sigma EA sigma EA kenapa dia 89.44, just check. Sigma bending tadi berapa? 78.26. Sigma EA 89. Okay, tau alternate. We don't have tau. Tau only have mean. Ini saya kena check balik. This is why, guys, ini kenapa dia 89.44? Because sigma EA is only sigma alternate only for bending. Bending already calculate 78.26, 78.26. Because sigma axial, I think ini little bit mungkin dia silap ni. Tak kelas, I think this solution, it think the, okay, since sigma axial load, because if you look at the question, the axial load remain constant unless it's saying something, the shafts of two pulley bearing 0.8, so the shaft is made, you want, okay, the working, okay, it's showing that is an axial load. Okay, that is an axial load. Okay, I think this question, I think the solution is wrong. Okay, nanti kita discuss about this. Guys, are you with me or not? This is supposed to be only because sigma A kan, sigma A only we have bending, right? I don't this, maybe this solution they put also the sigma axial stress plus 3.35 because when you go add it up, not supposed to add it up, I think it made a mistake, because when we go for apa tadi, sigma bending is 78.26 plus it take also the axial also is set as alternate. Axial don't have alternate, Axial is plus 3.35. Yeah, 81 points. Hold on, ini something, okay. Tak apa, kita discuss. Okay, tengok guys, kalau you tengok my case, you calculate for me. Ini sigma EA is 78.26. Try class. Are you with me? Okay, sigma EM is 22.95 megapascal. Okay. Class, sikit lagi. Are you with me or not? Class.
Yes, Doctor.
Alright, okay. Then we calculate the safety factor. Safety factor, if you look carefully, safety factor, sigma EA over your SN plus sigma EM over your SUT equal to 1 over your Goodman safety factor. And kalau the question ask either infinitely, you just check for Goodman only. No need to calculate for Langer, yielding no need. Okay, so sigma EA that we calculate, just now, 78.26. SN that we calculate from the beginning tadi, SN is endurance limit 195.72 plus sigma EM that we calculate is 22.95 over SUT just now from the material is SUT tadi berapa material? SUT is 638 megapascal equal to 1 over safety factor. So in this case, safety factor ada berapa? Cuba kira bagi saya. Boleh nampak my live video. Berapa safety factor ni? Are you watching class? Class, calculate it for me. 78.26 over, because sigma EA over SN. SN is 105.72. Sigma EA kita 78.26, but the solution put 89.44. I think it's kind of like because we don't have T ni, I think something wrong ni. Ini suppose sigma bending saja. Sigma A only bending. You don't have torsional stress unless it said that the torsional is the kind like fluctuating. No, torsional stress is remain as constant, yes, through times. You understand me or not? So what's my value here compared to the solution? Might be different. Mine
2.29.
2.29. So it means safe. So means safe. Okay. You just check. So 2.29 means safe. Okay. if you look the solution also failure against failure, good man, so 2.29, so yang itulah yang 2.29 dia punya, yang saya punya ni berapa? Ni 78.26 pula ni.
2.29, Doctor.
Yang ni dia letak 78.26 kan, nampak tak? Yang ini dia letak ini salah typo ni. Ini 70, betul lah saya buat ni. This is 78.26 kan. Dia wrongly put. Betul tak kelas? You understand what I'm talking about? So it means safe. Faham tak kelas? Kalau 2.29 it means shaft ni safe based on infinite life. Faham tak? Infinite life. It means this shaft rotate 10 million cycle. 1 revolution, 1 cycle. 10 to the power 6 even greater than that. The shaft safe. This system safe. Dia nama no failure happening. Okay, faham kelas? Too long taking your time. I understand nanti I share this recording of this video. So I go for, okay kelas? Boleh ada apa-apa question before I go for attendance?
So,
Hold on, siap.
Doctor,
Yeah.
Doctor, if it is a finite life, so what is it mean?
Apa dia? Pardon?
Kalau dia a finite life, bukan infinite life.
Kalau finite life, kalau your safety factor less than 1.
Oh,
Okay.
that's that one.
Kalau you punya safety factor just now we are using itu kan, sigma EA over SN plus EMN, we got this 2.29, it mean it go for infinite life. Kalau you say 0.7 something, less than 1, you boleh predict, it means this time designed for less than to the power 10 to the power 6, less than million cycles. So how do we do that? Based on we plot the log 10 tadi. Remember yang ni SUT, ini adalah straight line like this, macam ni, and dia straight macam tu. Ini adalah log 10 tau punya graph, log 10 punya graph. So infinite life is here. It means you boleh check you punya stress that you calculate berapa, you boleh check sini berapa dia punya cycle. Maybe 10, okay, this is 10 to the power of 5, so this is 10 to the power of 6. Because you punya stress that you calculate just now, stress sigma EA you punya tu, the stress that you calculate berapa, ini you punya fatigue strength you boleh predict. Sini yang you go, ada formula itu later class, kita akan discuss one. You can predict. That one will be on our next meeting. You can predict what cycles and it will break. You can predict it. Okay, but normally kita go for, we design like this. Safety factor, make sure that it's greater. 2.29 is good enough. Alright? Okay? Faham
Okay, thank you, Doctor.
Okay, I share you the, and then okay, scan your attendance class. Okay, Assalamualaikum warahmatullahi.
Thank you, Doctor.
Welcome.
Excuse me, doctor.
Thank you, Doctor.
Excuse me, doctor.
Thank you, Doctor.
Excuse me, doctor.
Ada apa question?
Yes. Doctor, do you need to only calculate for shoulder or also for nose?
Yeah. So yes, nanti I mentioned in the WhatsApp. Yeah, actually I just focus on shoulder. Better to get the picture, right? Because we don't have time, because it is a long one. This is a long one.
So we also need to calculate for
look at the
nose.
solution. Yeah, focus at the solution because I just want to give you idea. Look at the solution. The other part 2, it focus on the notch. Remember, notch is on the left, right?
Yeah.
Be careful. Notch is to the left of pulley A. Notch, we don't have torsional stress. Understand?
Yeah.
Look at the solution. Study the solution. If you look on the notch, the groove. Sorry, both is not the groove. On the left is groove, right? no torsional stress, because torsional stress only acting right after pulley. Pulley at A, right? Shoulder is up, yes, between. Shoulder have torsional. Shoulder is after the pulley, right? Before pulley B. But the groove on the left is before pulley. They don't have torsional stress. They only have axial stress and bending stress. Bending stress moment at that moment diagram, not at pulley A. Theorem Pythagoras at that groove position. Understand?
Yeah.
That's why look at the solution. I mentioned that in WhatsApp. The one I show you only we focus on the shoulder, but we have notch. Okay, but do not worry. Exam is not this long. This one, if you know this method, exam no problem. Okay.
Okay, doctor. Thank you.
Yeah.